Okay, folks, so here we are. We're going to be summarizing chapter 3. I think an important chapter, lots of really um, important ideas that we could study in a very simple setting of kind of a linear model with kind of Gaussian noise and Gaussian priors. So we could really see kind of what's happening without getting it all mixed up with the complexity of the model itself. So let's just kind of have a little run through of what we've discussed as a wrap up of the ground we've covered. Okay, so the main idea of this chapter was essentially using these having our outputs be linear in our inputs. So having weighting our d-dimensional inputs with these fixed weights that we learn from the data. And the key idea was that actually we don't have to live with kind of just our raw inputs. We can actually use arbitrary basis functions, so while still maintaining the benefits of linearity. So because what we care about is linearity in the weights, not the features themselves. So by doing that, we kind of open the door to allowing more useful features for the data that we're studying. So that was kind of the main idea. And we often saw it presented this way, right? So the weights doing a linear combination of the features being computed on the input. So that was, and then we discussed, using different types of weights, different types of features, Gaussian features, sigmoidal features, etc. And here are kind of pictures of that. And then we saw that, okay, so now we want to, given our features, we want to actually estimate the weights, and we initially started doing that by maximum likelihood. And in that case, it turned out that we ended up with, if we assume Gaussian additive noise, we ended up with a least squares regression problem. So here we had the likelihood of our weights, or the probability of generating some observation based on some weights. And we found, if we do this assuming independent observations, etc., that we ended up getting some normalization terms plus some kind of squared error terms. So we've got these kind of squared terms trying to explain each output as the same weighted combination of features applied to the corresponding input. So this became this doing maximum likelihood estimation then became kind of a least squares regression problem, finding these regression weights. And so we did that by essentially just setting the gradient of w to 0, and we ended up getting these maximum likelihood, the maximum likelihood solution, and they have various names, etc. The pseudo inverse came up, which is an important concept in that section. Cool. Okay, and then we spent some time, and I actually spent quite a bit of time, and my notes are available, on the geometry of least squares. And the main idea there was that when we're doing these regression problems, essentially what we're doing is we're taking kind of the vector of outputs and we're projecting them into the span of the features. And so our predicted output is that least squares projection onto that span. So that was kind of a very useful section and really good for building intuition about what's going on. Next was kind of sequential learning. So all of this stuff was done in batch, taking the entire data set and then updating your gradients using all of the data. But often in real life, you can't actually do this either because the data is not fully available or it's too big. And so we talked a little bit about how to do this sequentially, which was essentially you have your weights and you modify them by a small amount based on the contribution from each data point, and it ends up kind of looking something like this, right? So you've got your current weights, your some kind of step size, and the error on the current data point given the weights that you have. So kind of very natural idea that you would probably come up with yourself if you want to do it. You just decompose your error into the contributions from each data point, and then you add up those contributions to the weights individually rather than all at once. The next topic was we talked about regularization, which was, okay, so we've been doing maximum likelihood. What if we want to add some prior on the weights? And we discussed different kinds of priors. So the most common one is this kind of just a squared prior, which will tend to shrink the weights, or produce kind of weight decay when we talk about why that is. So we'll kind of shrink the weights towards, in this case, kind of 0, which is their prior value. But there are other possibilities, so we could kind of use other types of priors. So, for example, priors like this, the L1 priors, or the even sharper, will tend to promote kind of sparser solutions. So, when we use the sum of squares, we'll never shrink any weights to identical to 0. We'll just scale them down. Whereas, for example, with the L1 priors, or even the non-convex versions, you will actually get situations where the weights can be shrunk down to 0, and that can be useful for like variable, identifying which variables are important, etc. So yeah, that was kind of the lasso and the sparse models, and there was kind of a good. I hope you understood this picture about what's going on, why the L1 priors and sharper will tend to produce sparse solutions. That's a really good one for building intuition. We then looked at, okay, well, we've been looking at kind of just single output each time. What about having multiple outputs? But we found that, I think kind of remarkably for the class of simple models that we have, that the problem actually reduces to just having a bunch of parallel regression problems, one for each one of the outputs. So you have kind of a separate set of weights, all working on the same feature set, and you can just learn them independently. So that's kind of a nice property of our particular model. And so it just meant that for the rest of the chapter, we're gonna stick with the scalar, assuming that we're mapping inputs to scalar outputs, and that's actually going to be, that won't be a problem, because the full problem is just a bunch of parallel subproblems like that. Okay, so that was the end of section 1. Section 2 was about the bias-variance decomposition, which is kind of a frequentist approach to kind of model complexity and how to control that. And the main lesson of this section was that we can actually describe the loss, the expected loss of an estimator as being composed of its squared bias plus its variance plus some irreducible noise term. And so then we could understand that estimators that are too simple, they don't have much variance across data sets, because their predictions are all very similar, but they have kind of a large bias. Whereas estimators that are actually very, very complex, that are very powerful, their bias will be 0. They'll be able to capture the data on average, but they'll have a lot of variance over data sets. And it was very important to kind of keep in mind that all these averages are being done over data sets. So that was kind of a subtlety that we needed to keep in mind. But this will essentially give us some insight into how into the effects of kind of model complexity on the loss. And so we use that to kind of consider what happens in the case of let's say in this case, I guess the regularization is quite high. Here you have regularization which is quite low. You get lots of variance across data sets. Yeah, and then this was kind of a very useful plot here showing our I guess is going to be our test area here, but our bias plus variance term being the sum of the bias squared plus the variance, so kind of verifying that expression. Okay. And then so after having kind of looked at the frequentist approach, with a little bit of Bayesian stuff with the priors on the weights, now we start looking at the Bayesian approach to linear regression. So having a prior on the weights and then a posterior on the weights. So not reporting kind of a point estimate, but actually trying to keep the whole a whole uncertainty on the weights, and keeping that the whole way through. So and what we did throughout was essentially put a Gaussian prior on these weights, and then we look at if that's the case, then given our existing model of the likelihood of the weights, how they produce the outputs, we end up with a posterior on the weight that is also again going to be Gaussian, but with this updated form of the mean and the covariance. And for most of the rest of the chapter, we just assume a simplified form for this. And what we kind of wanted to point out in this section was that, and I think it's actually coming up, yeah, that we can actually use the posterior as the prior for the next stage. So we can kind of do kind of sequential estimation as we get, kind of very natural way as we get more data points. So this was kind of our original prior. Here was the data when we don't have any information. As we get new data point, this prior combines with the likelihood to give a new posterior, which we then use as a new prior for the next stage. So this is kind of a very natural way in which Bayesian sequential estimation pops up. So that's what that was about. Next, we talked about this important idea of the predictive distribution. So again, in the Bayesian approach, so once you have that posterior on the weight, so what do you do with it, right? In kind of a frequentist approach, you might want to say, well, I'll just take the most likely value, the posterior mode, and use that to make estimates. But actually, in the Bayesian approach, what you're supposed to do is you use the whole distribution that you have, and you kind of add up the contributions for every one of those weights, but weighted by its posterior probability. So this is kind of the marginalizing out the weights. This is kind of a very, I'm actually going to even highlight this, very important aspect of the Bayesian approach. I think it's one of the key aspects that, if we want to make a prediction, we don't just stick with one weight, right? We have the whole point of the Bayesian approach is to keep all of your uncertainty and use it in the correct way. So here we're just going to average the contribution from each of the weights weighted by its probability to producing the output, and that gives us the predictive distribution here. And we see that again later, and when we at the very last section where we're talking about what we really should also do is add an alpha and a beta term here, and actually integrate over our hyperparameters as well. But that's not what we're doing in the first instance here. And we find that if we just focus on the weights, because everything's Gaussian, we get a nice Gaussian a Gaussian as our predictive distribution. And yeah, so here's kind of what that looks like for different points. And you notice that on average, the variance at each point is kind of lowest around data points. It doesn't always have to be the case, but it will often be the case if the points are farther apart than the features you're using. And that's kind of what we saw there. Okay. And then, so in 3.33, we actually touched on a very interesting notion that we're going to see more of, I think, in chapters 6 and 7, where we saw that we can actually think of our kind of our estimation or our prediction problem. We can actually think of doing it, instead of doing it as we're going to weight some features, we can see it equivalently as kind of interpolating our inputs according to this kind of similarity kernel. And the similarity kernel, we call the equivalent kernel, and it kind of told you that how much neighboring points influence each other, and that of course depends on the basis function you're using, and also kind of the covariance of the data. And so just kind of gives us kind of a new perspective on how we actually do regression, a perspective that's kind of focused on the input data itself, and sees it as a smoothing problem or as kind of an interpolation problem. Yeah, and so we can kind of work out what these kernels look like for different types of basis functions. So I think this is like a polynomial basis, and this is maybe a sigmoidal basis. And nevertheless, you see that basically the points that really affect or are affected by equivalently the value at 0 are just the ones that are kind of nearby in kind of this low lobe, and the points that are farther out don't so much, and that just depends on the properties of that similarity kernel. And that similarity kernel also determines the covariance of different points, so how much predictions at different points affect each other. So I think it's a very useful perspective that's going to come up again, and I think we'll spend whole chapters on it around chapter 6 or so. Okay. Oh yeah, and this was kind of an important point, that instead of we can instead define the localized kernel directly and use this to make predictions for new input vectors, right? So that was kind of a cool thing, right? And why go through this process where we could, if you have knowledge about what that kernel should be, you could just use it directly to make predictions. And this is kind of useful when you're talking about things like let's say strings or more complicated objects, where it might be hard to it might be easier to just say, express your notion of how similar two strings are, rather than trying to kind of come up with it through some features and their interactions with their covariance. But it does turn out that for all these kernels, they can all be equivalently expressed as overlaps of features. But the cool thing about this approach, which we'll see, I'm sure, in chapter 6, is that actually we don't have to work with these features. Like, they're there always in the background, and they're useful often for doing proofs and things. But you can equivalently just work with the kernels themselves, and that can often be a lot simpler and more kind of directly connected to your problem. So a nice taste of that, which we'll see again in chapter 6. Okay, so then the next part was we talked about the Bayesian model comparison, and the main lesson here was that the Bayesian approach, by integrating over parameters, the parameter space, just like we saw, it naturally penalizes more complex models, because more complex models can essentially predict a larger variety of data sets. So any particular data, and because those predictions are kind of spread evenly and they have to kind of be normalized, if you can predict more data sets, then your prediction for any particular data set is going to be weighted down. And so more complicated models that can kind of capture larger sets of data will naturally carry a penalty with them, based precisely on their kind of complexity. So is the model evidence term, which is the probability of the data given a model, which kind of integrates over the parameters of the model. The marginal likelihood. So the model evidence, something's called the marginal likelihood. We saw this in the very last section as well. One of the kind of confusing aspects of terminology, but that's fine. The ratio of model evidences is the Bayes factor. Okay. Yeah, there's kind of a couple of cool pictures here. So, for example, here that we saw that the probability of the data given a model is equal to how well that a particular data set is explained by the parameters of that model. So that's system of goodness of fit term. But then there's this kind of ratio of how tight the posterior is over the prior, and this term will actually tend to penalize the more complex models, because, for example, the more complex models will have a wider prior. So this term will actually be much more negative, for example, or maybe this term will be very very sharp. So this will be very small. And those will kind of collude to penalize more complex models. Yeah, so if those parameters are finely tuned to the data and the posterior distribution, the penalty term is large, and that's this one right here. And then finally, there was kind of this interesting picture again expressing the same idea, that basically the reason why models of kind of intermediate complexity are favored is because when the model is too simple, the probability of a particular data set that you have is 0, so the model can't capture it. If it's too complex, well, your data set can be captured, but so can many others, and the probability, because the probabilities are normalized, are correspondingly reduced. So the kind of intermediate models tend to be the ones that are, or the ones that have the appropriate level of complexity, and it's all kind of just done very naturally, which is, I think, one of my favorite things about the Bayesian approach. It captures this model complexity very naturally. You don't have to learn a whole separate thing or bring in some ad hoc methods, just capture it naturally. Cool. Yeah. Bayes factor. Yeah. Exactly. So this was saying the point that we have we have this quantity here that represents the relative evidences of two models, and what we're showing here is that if one of the model happens to be correct, then on average over data, not on a particular data set, on a particular data set, maybe model 2, which is the incorrect one, will win out, but on average, the correct model will win, which says that the Bayes factor on average will favor the correct model, which is a very nice property. Okay. All right. So finally, the very last section, which was kind of a bit of a technical section, was wanting to kind of do the full Bayesian thing, right? So like we wanted to get the predictive distribution, but now also averaging over not just the parameters, but the hyperparameters as well. And we saw that this, and when this is kind of intractable, which even for our simple model, where everything's Gaussian, when this bit is Gaussian, it is, we need to come up with some approximations. And the approximation that we used in this section was to basically replace this with the delta function at its maxima. And this was kind of called the evidence approximation, because this guy is going to be the model evidence. So we're going to approximate this by a delta function at its peak, and then that'll give us a tractable, analytically tractable integral that then we can use to approximate our the predictive distribution that we're after. So essentially, what we did was, in the first section, we talked about this function. We came up with a closed form expression for it. We talked about how that can actually be seen as a balance between goodness of fit and kind of these Bayes factors, these Occam factors, balancing complexity. We saw that, okay, in this, just viewing this function on its own, we could use it to actually predict, without any test data, just on the training data alone, the order of our model. So remember, in this model that we essentially have, I would say we have two parameters that control complexity. We have alpha, which is how much we are penalizing large weights, but we also have this, like, how many parameters do you have, how many weights do you have? And so we saw that if you somehow knew alpha and beta, which for most of the section, the whole point is that we don't know them, but if you did, and you wanted to determine the model order, well, normally, in kind of maybe the frequentist way, you would have to, like, have a training data set, test data sets, vary alpha, and then try to, fit for different, for different alphas, like find some weights, and then compute the predictions on some held out data, and then find the minimum. It's a big ordeal. Whereas here, we can actually just use our expression here for fixed alpha and beta, but try different m's, and then see where we get the largest model evidence. And we saw that it has this kind of very interesting shape due to the fact that, for our sinusoidal data, there is kind of a sweet spot of where your goodness of fit increases and your complexity penalty isn't quite so high, so that it turns out a cubic function kind of which agrees with our intuition, is also what comes out of this approach. Again, you have to know alpha and beta, but I think at least a fun toy example to look at and see how it plays out. So that's what we did. Then we talked about maximizing this evidence function to get the alphas and betas. We saw that we couldn't do this in closed form, so we ended up with these kind of iterative approximations, iterative procedures for doing so. That was for alpha, and for beta, this is kind of the noise precision, basically. And then we encountered this interesting quantity, which turned out in the final section that we could interpret as how many parameters our data actually kind of constrains, how many parameters it actually provides enough data for, and how many it doesn't. And we saw that actually shows up as in the bottom here, in this kind of in exactly the same way that it does. Exactly the same way as it does, when we're doing map estimation, let's say, of the variance, where there's a -1 term at the bottom. Here now we've got a minus gamma term at the bottom, corresponding to the effective number of parameters that we're learning, and that gamma parameter, we saw, by looking at the contours of the maximum likelihood function, where that comes from, and how it kind of tells you how much of your data is being, how many of your parameters are being constrained by data, which I thought was really really cool. And yeah, based on some of those insights, and we actually came up with kind of very simplified approximations for alpha and beta, which you don't have to work out the Hessians or anything. You can just essentially estimate alpha as the variance of the weights, of the maximum likelihood weights, and beta as the variance of the maximum likelihood residuals. So in the limit of large data. So that was cool. And then we saw that, okay, like at least in one test of this whole procedure, does it actually work? Is that we saw that if we pick alpha when we know beta, if we pick alpha the way that this procedure says, so again, without using any test data or anything, we actually end up doing nearly as well, almost optimally in terms of test error. So it kind of suggests that this approach is actually promising and is useful for picking these hyperparameters and approximating your predictive distribution that way. So that was it. And I think the very last section, we just talked about the limitations of fixed basis functions, basically due to the fact that as dimensionality increases, because you can't adjust your basis functions once you see the data, you're going to need an exponentially large number of basis functions. And so then we just briefly spoke about how support vector machines and neural networks and essentially methods that can be adaptive can overcome these limitations, and we'll see more of that in future chapters. And so that was it. Hope you guys learned a lot. I sure did, again, just preparing this material. So let me know if you liked it or if you didn't. And yeah, as always, love to hear your comments. And yeah, hope to see you in the next video. I think for the next video, we're actually going to switch gears and go to chapter 12 based on some teaching obligations I have at work. So we're going to change gears for a bit. But in the meantime, hope you enjoyed Bayesian linear regression, and yeah, talk to you next time. Bye.